Hi, I'm Anunay Kulshrestha from the Center for Information Technology Policy at Princeton University. In this paper, we formalized the problem of detecting harmful media in the end-to-end encrypted setting. Our work is motivated by the contemporary debate on appropriate responses to child sexual abuse material, terrorist recruiting imagery, and disinformation shared over end-to-end encrypted channels. We propose protocols that provide the necessary security and privacy guarantees. We then implement and benchmark them to illustrate their practicality. We also discuss limitations of our proposal. Popular messaging services like WhatsApp, Signal, etc. are now end-to-end encrypted. This provides an invaluable defense against security threats, privacy risks, illegitimate surveillance, and other human rights abuses. However, some users use them to share child sexual abuse material or CSAM, terrorist recruiting imagery, or disinformation. These are different types of harmful content, and their detection should evoke different responses from the service provider, from notifying law enforcement in the case of CSAM to displaying a warning label in case of disinformation. In non-end-to-end encrypted services, perceptual hash matching is the canonical method used to identify harmful media, which I will discuss shortly. Nonprofits like the National Center for Missing and Exploited Children and coalitions like the Global Internet Forum to Counter Terrorism coordinate clearinghouses of perceptual hash datasets of known harmful content. But none of this works in the end-to-end encrypted setting, where the service provider simply cannot access content. In particular, the service provider cannot even compute the perceptual hash. Within this framework, law enforcement agencies have argued for pausing deployment of end-to-end encryption until we can detect these harmful media, while civil society groups and academics remain skeptical about the technical feasibility of privacy-preserving detection. Perceptual hash functions, or PHFs, produce hashes of media such that perceptually similar media have similar perceptual hashes in terms of hamming distance. However, this is not always true in practice, as illustrated by the example. Here we use phash, a popular PHF, to generate 256-bit hashes. Phash is clearly resilient to addition of Gaussian noise, but not to rotation. In perceptual hash matching, a client holds some media I such that X is the k-bit perceptual hash of I. We assume that the PHF is public, as most are. Due to the absence of the avalanche effect, perceptual hashes may reveal information about their pre-images. So we consider the perceptual hash X to be as private as the pre-image I itself. A server holds set B of perceptual hashes that are known to correspond to harmful media. The security of B is crucial, as knowledge of its elements can disclose law enforcement sources or methods and can be used to circumvent detection. Similarity is defined via hamming distance, and a threshold is selected empirically. PHM systems seek to answer either exact queries of the kind, is X in B, or approximate queries of the kind, is there Y in B that is similar enough to X? If a match is detected, the service provider can take appropriate action. We devise privacy-preserving protocols that realize this functionality. Here's how we formalize the problem. Similar to exact and approximate PHM, we define PEMC and PAMC. A PEMC protocol reveals whether X is in B and nothing else. Similarly, a PAMC protocol reveals whether there exists some Y in B that is similar enough to X and nothing else. Either party can be delegated to learn the result. Our protocols guarantee client and server privacy of X and B respectively. Perceptual hash matching systems in general do not provide security against malicious clients, who could simply encrypt harmful media out of band before sending. PHM systems can detect instances of sharing with only modest efforts at evasion or when senders are not aware that shared content is harmful. Similarly, our protocols protect against semi-honest parties. A semi-honest client learns no information about B, and a semi-honest server learns no information about X, other than the protocol output if it is the delegated party. We do, however, provide security against malicious clients that attempt to cheat in server-revealing versions of the protocols. In particular, if X is in B, or if there is a Y that is similar enough, no malicious client can prove otherwise without being detected by the server. Before we dive into the details, I would like to discuss some major limitations of the work that follows. Our protocols cannot guarantee that the set B only contains hashes of harmful media, so the potential for abuse is immense. Perceptual hash matching itself causes false positives, which break privacy guarantees for honest users. Deployment of these protocols would clearly increase the attack surface for end-to-end encrypted services via possible side channels and may even have adverse externalities. For example, implementation in a democratic jurisdiction may undermine arguments in favor of end-to-end encryption in other countries. We do not take a position on the question of deployment of such protocols, including ours. Our goal is to spark discussion and future work by formalizing the problem area and demonstrating technically feasible protocols. Private membership computation is adjacent to prior work on privacy-preserving matching and content moderation in the end-to-end encrypted setting. Tyagi et al. And others have devised protocols for message franking, which allow service providers to prove that a reported message was indeed sent by the alleged sender. Private membership tests, or PMT, are client-revealing variants of private exact membership computation that do not protect the privacy of service set B. Private biometric authentication protocols allow private Hamming distance computation, albeit for much smaller sets B. Here's a brief overview of our protocols. For simplicity, I'm going to describe server-revealing variants of our protocols. We discuss client-revealing versions in the paper. The parties first use locality-sensitive hashing to reduce the hash search space. Then they use private information retrieval to retrieve homomorphically encrypted hashes from this reduced space without revealing any information about X or B. Now the parties can run private equality tests using these encrypted hashes. At this point, for PEMC, the server can compute the result. For PAMC though, we need an additional step that hides the Hamming distance from the server, a private threshold comparison that we construct using a privacy-preserving comparison protocol. We don't formally define locality-sensitive hashing or LSH here, but intuitively it allows us to partition set B into buckets such that the probability that two hashes will be mapped to the same bucket is proportional to their similarity score. For exact membership, we define the L-bit locality-sensitive hash of a k-bit string as its L-bit prefix. However, this doesn't work very well for approximate membership, as it preserves locality if and only if the L-bit prefixes match. To reduce false negatives in PAMC, we use miniature perceptual hashes as locality-sensitive hashes themselves. Intuitively, if two perceptual hashes with a large bit size are close enough, then the same PHF will produce shorter perceptual hashes of the same media that coincide with high probability, thus putting both pre-images in the same bucket. The server computes the locality-sensitive hash of every string y in B. Suppose the LSH is the L-bit value I. The server then adds an encryption of y to the set Ci. After doing this for all strings y in B, the server has an LSH index int that maps L-bit values to sets of ciphertexts. The client can also compute the LSH of x. If x is in B, it will always be mapped to bucket L of x. If something similar to x is in B, it is also mapped to bucket L of x with high probability. So the hash search space is reduced to just that bucket of ciphertext. A computationally private information retrieval protocol, or PIR, allows a client to retrieve an element from many held by a server without revealing its element choice. Coming back to our protocol, the client can retrieve CJ via PIR. It's crucial to hide J from the server because it reveals the LSH of X. Now the two parties can engage in private exact equality tests over all perceptual hashes in the bucket. We want to determine whether two ciphertexts decrypt to the same plaintext without revealing anything else. For now, assume that the server has just one hash Y. It picks an Al-Gamal key pair, PKSK, sends PK and CY, an encryption of Y to the client. The client encrypts -X using PK, adds the ciphertext to CY, chooses randomizer R, and multiplies the result with it. Now, due to the partial homomorphism of Al-Gamal encryption, C is actually an encryption of R times Y minus X, which is 0 if and only if X equals Y. Client's randomization using R ensures that if X does not equal Y, decrypting C doesn't reveal anything about X to the server. In the approximate case, we need more than partial homomorphism. We want to find a homomorphic transform zeta that allows us to compute the Hamming distance between two encrypted bit strings without revealing anything else. In the BFP cryptosystem, plaintexts are polynomials, so we define two ways to pack a k-bit string into a polynomial, pack1 and pack2. We also define two polynomials, jx and jy, which are constants based on k and n. We build on work by Yasuda et al. From 2015, who used this technique with somewhat homomorphic encryption. Again, the server generates a key pair, sends PK to the client along with an encryption CY of Y using packing 2 and PK. The client generates CX using packing 1, computes zeta CX CY, and sends that to the server. The server decrypts CR and checks the constant term, which is the required Hamming distance. The issue is that the server learns the Hamming distance while we only want to reveal whether the distance is at most some threshold delta H. We use additive randomization to prevent the server from learning the Hamming distance. Prior work by Osachi et al. Used expensive oblivious transfer to undo the randomization. We use privacy-preserving comparison, which makes the protocol much more efficient. The client chooses randomizer polynomial R, and now CR is zeta CA-CB plus R. When the server decrypts CR, it learns the Hamming distance plus R of 0. We use a PPC protocol that returns false if the client's value nu C is at least as big as the server's value nu S. If nu C is equal to R of 0 and nu S is equal to Pxy of 0 minus delta H, the protocol returns false if and only if the Hamming distance is at most delta H. Thus, the server only learns whether the distance was at most delta H but not the distance itself. Now we put it all together. The two parties compute private equality tests for each encrypted hash in the client's bucket of interest I equals L of X. The server does not learn I, so it cannot tell what ciphertext was retrieved. Due to client randomization, no information about X is revealed to the server if X is not in B. But if any of these equality tests return true, X is indeed in B. Due to PIR and the threshold comparison, we cannot let either party generate keys for PAMC, or else they may be able to decrypt something they should not be able to. So we use a distributed key generation protocol for BFP that results in collective public key PKAG. Both parties can jointly delegate either party to decrypt ciphertext encrypted under PKAG using a collective key switching protocol. Again, we run the approximate equality test once for each hash in bucket I. In the paper, we discuss optimizations that reduce communication cost by packing multiple hashes into one BFP plaintext polynomial. We implemented our protocols in C++ using Microsoft Seal, SealPIR, NTL, and Botan. The code will be on GitHub. We ran benchmarks on a 6-core Intel i7 using 256-bit hashes, a 20-bit LSH family, and SealPIR parameters N and D, 2048 and 2 respectively, with both parties running locally. These are preliminary benchmarks, and we are aware of some known optimizations that could improve both computation and communication costs. Thank you for watching, and please direct any questions to Anunay at cs.princeton.edu.